So today we will talk about the three-phase diode rectifiers. They are quite common in industrial applications where you have a three-phase supply, but you need to either direct the DC output, or maybe you want to convert that DC output to other frequencies such as a variable frequency drive. So in those cases, three-phase diode rectifiers are commonly used. So let's start using a simple example. So the first topology that we will look at is three-phase half-wave rectifier. Okay, we will go through the full-wave rectifier, but let's look at the circuit of a half-wave rectifier. So in the half-wave rectifier, and it doesn't have to be basically three-phase. It can be like any phase, and here you see a representation. So in that one you have one phase, two phase, and it can go up to m phases in this case, and you have just one diode connected to each phase, and the common points of these diodes are connected to your load. So you have first phase, second phase, third phase. So from the point of diode 1, okay, you have the output voltage here. Whenever input voltage is larger, the voltage of the first phase is larger than V out, then the D1 will get into the conduction. So whenever second phase is larger than output voltage, then it will get into the conduction. So if any of those diodes, let's say if V3 is conducting, okay, D3 is conducting, so that voltage will be equal to V3, and then V1 will get into the conduction. If V1 is larger than V3, then that diode will be off, then the first diode will be in conduction. So if you just simplify that algorithm, so the phase with the largest voltage, it can be V1, V2, V3, will get into the conduction, and then the output voltage will be equal to that one. And of course, I assume again you have a very large inductive load, so the current can be assumed like a DC current. Okay, so let's look at that case for a three-phase application. So here we just represent V1, V2, and V3. Okay, so I have the first phase voltage, second phase voltage, third phase voltage, and so on. So they are all 120 degrees separated from each other. So in this region, okay, draw that one. So in this region you can see V1 is larger than V2. Okay, in that range V2 is negative. Yes, here it is positive, but it is still smaller than V1. And the same thing is true for V3, so this is smaller than V1. So in that one you have, let me write it here, D1 is on. Okay, so in this region D1 is on. However, at that instant, let me draw it with red. So now V2 gets larger voltage. So at that instant V1 gets smaller, but V2 becomes larger. So at that instant you have D2 is on, right? If you just remember the previous slide, so at first D1 was conducting, then it becomes off, then it is the second diode's turn, then it will be off, then it will be the third diode's off. So they will be in conduction mode in sequences. So afterward we have the third phase is larger, so which corresponds to here. I think that line is shifted, it should be somewhere here. So we have the third diode is on. Okay, so what is the conduction time for all of those? Here you can see again that one is V1, so that is V1, and that point is cycle of any of those voltages. So if that period is 360 degrees 2p, so each of these conduction periods will be 2p over 3 or 120 degrees. So these all are in conduction mode for 2p over 3. Right. So how can we calculate? I mean, if you are convinced with that waveform, then our voltage waveform, this is our output voltage waveform, so it is equal to V1 for that one, and it is equal to V2, and it is equal to V3 for that one. So you can see I have a rectified voltage, and the average value, we will calculate that one, should be somewhere here, right? So one of the biggest advantage compared to the single phase rectifier, remember in the single phase rectifier you have a waveform like that, so you have a peak square root 2 Vs RMS, and then it have that peak and it goes down to 0 volts, right? However, if you use a three-phase rectifier, so the minimum voltage is actually higher than 0 volts, so it doesn't go down to 0 volts. So that is good, because if you would like to put some capacitor filter for that one, so you have to, you know, put quite a large capacitor to compensate for that area. So this is capacitor. However, in that one, the ripples, you know, even if you don't put any capacitor, the ripple will be like that, and it will be much simpler to filter out that small component compared to, you know, square root 2 Vs to 0 volts. So that is, you know, one of the largest advantages of the three-phase rectifier. So then the question is, how can we calculate the V average? Okay, so let's look at that simplification. I have the same figure, I will use it for calculations. So let me draw that line, right? And if this is 0, this is, let's say, V1 again, this is V2, this is V3, right? So V1 goes up to here, and this part is my period, so this is 2p, let's say here. So my question is, so again you can see from the previous figure that the most critical parts are those points where these two phase voltages are equal to each other. So my question is, how many degrees are those points? Okay, that is again an important information, and you should be like really familiar with that one. If this is 2p, that is p. So, and here you can see this is 90 degrees, p over 2. You can say, I mean, is it 30 degrees, is it 45 degrees, or is it 60 degrees? So let me write it here. I don't know, like a quick quiz question. Okay, so you can calculate it trigonometrically, or, you know, just remember that one. This is 30 degrees, or that point is pi over 6. Okay, the point where V1 is equal to V3. And from symmetry, you can say that area is also 30 degrees, so this is 5 pi over 6, or this is 150 degrees, right? Why that is important? Because if I want to calculate the average voltage, my output voltage waveform will be like that, right? Let me draw it again. So if I'm going to calculate the average voltage, I will calculate the area under that curve. Okay, for 2p I will calculate the red area, then I will divide it by the period. Okay, remember V average is equal to 1 over 2p 0 to 2p of V output dt. Okay, I can get the average voltage. And again, from symmetry you can see that, okay, that thing, that red area is adding 3 of those things. I have 1, I have 2, and I have, you can either get that part to here, or you can get the other part. That region is symmetrical to here, so you have 3 of those things. So if I calculate the red area, green area, if I calculate the green area and I can multiply it by 3, I can get the all red area. Then I can divide it by 2p and get the average voltage. So let's try to make that calculation. So let me get rid of myself. So in that case you will have VDC, okay, VDC is equal to, I'm calculating the green area first, okay, it is 1 over 2p over 3, because that part is 2p over 3, okay, from 0 to, I'm sorry, not 0, right, pi over 6 to 5 pi over 6. I'm trying to get that area, and it is square root 2 Vs times sine omega t d omega t, right? Maybe you are wondering why I did that one. That part is the green area, so I am dividing it by 2p over 3. Or what you can do is you can have 5p over 6 square root 2 Vs sine omega t d omega t. So that part is the green area. I have 3 of those things, and you can divide it either by 2p, 1 green area, 2 green area, 3 green area, or if you can get the average voltage over that period, which is the integral divided by 2p over 3, that is symmetrical, so you will have the same voltage. It is the same thing. Anyway, so how can I calculate that area? So what is, maybe another question should be write that. So if you have, this is pi over 6, 5 pi over 6, okay, so what is that area if this is 1? The all sinusoid, remember, was 2, and what is that area? So let's try to calculate that one. So those two are constants, so we can get them out. Square root 2 Vs divided by 2p over 3, okay, then the sine, the integral of sine is not cosine, minus cosine, okay, you make that mistake quite a lot in the exams. So, and from pi over 6 to 5 pi over 6, right? So what is, let me write that one again, calculate that one. So what is cosine 5 pi over 6? So if you maybe remember, so if this is 150 degrees, so this is 30 degrees, so cosine is that point, so you can see it is minus square root 3 over 2, okay, so this is minus, so it is minus minus, it is square root 2 over 2 minus, okay, minus again square root is the same for 30 degrees, cosine 30 degrees is square root over 2, and they just add up and you get rid of the square root. So you get rid of the 2 and 3 comes here, so it becomes 3 square root 2 vs divided by 2p times square root 3. So if this is the peak, that area, you can just remember that one, square root 3. All area is 2, and that from 30 degrees to 150 degrees is like 1.78, something like that. So anyway, and if you write that one, it is 3 square root 6 divided by 2p times Vs. Okay, so this is your average voltage, and that one is like 1 over 15 Vs RMS. Okay, again, this is the RMS voltage. So this is your output voltage, 3 square root 6 divided by 2 VRMS, and it is 1.17 VRMS. Okay, if you just compare it with the single phase rectifier, remember, single phase rectifier, it was 2 square root 2 divided by pi, or 0.V SRMS, and it was 207 volts. And if you have a 3 phase, this is half bridge rectifier, this is 3 square root 6 divided by 2p times VRMS, or it is equal to 1.17 VRMS, and that is equal to 269 volts. Okay, so if you have used a single phase rectifier, you can get an average, this is the DC, average DC, 207 volts, but if you use a half bridge rectifier, it is 269 volts, so it is kind of increased from the single phase rectifier. Okay, but actually half wave rectifiers are rarely used, and the problem is, this is just a exercise, but what is the problem with those half wave rectifiers? So for half wave rectifiers, actually the biggest problem is the current waveform. What does it mean? We will see it in the following weeks, but just as an intro, so you have a single diode from V1, and that D1 is get into the conduction for 120 degrees, right? So if I plot I1, okay, I1, it will be off, then it will be on, then it will be off for some time, and that period is 120 degrees. Yes, it is on, and again, if I assume like a constant DC, then it will be carrying DC current. But the problem is you have just a single diode. There is no way that there will be some negative current in that direction, right? So at most the current will be 0, and when it is on, you will have DC, or even if it is like a resistive load, if this is a resistive load, then it will be maybe that kind of shape for the current. But at the end of the day, you don't have any negative components, right? You don't have any ways to draw negative currents. As a result, if you just get the average voltage, okay, if this is I average, then you will have some DC component. So that means you are trying to draw some DC component from AC grid, and that has bad consequences in your transformers, saturation, or in other systems. So usually that is like one of the largest disadvantage of the half wave rectifiers, but this is just an intro to full wave rectifiers.